Today we will start a topic eigenvalues, and we will use numerical methods to find eigenvalues. I am starting with formal definition. Eigenvalues play an important role in many applications. So let A be any linear transformation which is represented by a matrix, and if x is a non-zero vector, so that a of x equal to lambda of x, then this number lambda is called eigenvalue, and this number lambda is also called characteristics value, and this vector x is called eigenvector. Eigenvalue and eigenvector, they always occur in pairs. So if there is an eigenvalue, there is also an eigenvector. And formally you can find by solving this equation. So let us say this is a minus lambda I x equal to 0. This is a homogeneous system of equations, and this will have a non-trivial solution x if determinant of coefficient matrix is 0. So by solving this determinant a minus lambda, you can find eigenvalue, and if a is an n cross n matrix, then you will get an n degree polynomial like this. And solving to this polynomial not an easy task. Let us say we have a 10 cross 10 matrix, then you will get a polynomial of degree 10. So in this topic we will study numerical methods which find eigenvalue without solving these kind of equations. So firstly, I'll talk about few properties of eigenvalues and eigenvectors. Firstly, we have ax equal to lambda x. So you can multiply x with any number, say mx. So if x is an eigenvector, so is mx. Okay. So if x is an eigenvector, so any multiple of eigenvector is also an eigenvector. And secondly, you know that sum of all eigenvalues of matrix A, that is equal to trace of matrix A. And what is trace? This is sum of diagonal entries. So we can use this property, sum of all traces, sum of all diagonal entries. So we can use these properties to capture eigenvalues. Let us say I have a 3 cross 3 matrix, I know 2 eigenvalue, and third I can find from this property that sum of all eigenvalue, that is equal to trace of matrix. Also, if we have ax equal to lambda of x, then pre-multiplying A inverse on both sides, okay, then I can write it as A inverse x equal to 1 by lambda x. So if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of A inverse, and eigenvector remains same. Okay, so if lambda is an eigenvalue of A, then 1 by lambda is an eigenvalue of matrix A inverse with same eigenvector x. Also we can write, if A matrix A has eigenvalue lambda with eigenvector x, then I can write Ax equal to lambda of x. Then this can be written as, I can subtract k times x or ix on both sides, so we can write lambda x minus kx. Here k is a number. Okay, so I have written it matrix notation, so identity is 1, so you can write kx is kix. Then in left hand side you can take x outside, so this is A minus k times, if there is some confusion you can write kx. Okay, and then k in matrix notation I can write A minus ki. So you can take lambda minus k, then x outside. So by definition, so you can see from this that if A has eigenvalue lambda, then A minus ki has eigenvalue lambda minus k with same eigenvector x. Further, you can, from this you can also write A minus ki inverse x equal to 1 by lambda minus kx. So A minus ki inverse has eigenvalue 1 by lambda minus k. Okay, so k is any non-zero number. Okay, and so in this topic we will study two numerical methods to find eigenvalues. First is power method and second one is known as QR algorithm. So I am starting with power method. So this method picks dominant eigenvalue. Dominance means the eigenvalue which has largest magnitude. Let us say matrix A has eigenvalues. A is a 3 cross 3. It has eigenvalue 1, 2 and 3. Then this 3 is called dominant. Okay, so this is largest in magnitude. So this is an iterative method which picks dominant eigenvalue and also eigenvector, corresponding eigenvector. So okay, so advantage of method is this, that you not only get eigenvalue but also we get corresponding eigenvector. And we will see further that by modifying this method we can pick other eigenvalues. So this is an iterative method, like we have studied before, many iterative methods like fixed point, Gauss idle, etc. Iterative method, and it picks dominant eigenvalue and corresponding eigenvector. So I am writing its algorithm. So this is just based on the definition that we are using for eigenvalue. So Ax equal to lambda of x. Okay, since we don't know x, so we start with some initial guess. So let us start with initial guess of eigenvector, which I am writing x0. You can take it like 1 1 1 1, okay, and it should be non-zero. And one more condition is that its norm should be 1. So we can take like 1 1 1 0 1 0 0 1, anything you can take, okay. Then you multiply this initial guess with matrix and you will get some column vector, say that is y1. And now we will scale y1 so that norm of y1 is also 1. Okay, so new approximation x1 is that we take y1 and we divide y1 with its norm. So we have scaled y1, so that new x1 will satisfy the same condition that norm of x1, that is largest component of x1, is less than or equal to 1. Now we repeat the procedure. So we next find y2. Again we multiply a with x1, and we find x2 from y2 by taking its norm, by dividing with the norm of y2, and so on. Okay, so we repeat the procedure, and after some time you will see that these x1 x2 they will converge to these xk, they will converge to dominant eigenvector. Dominant eigenvector is the eigenvector corresponding to dominant eigenvalue, and the numbers we are dividing with, that is called norm of that yk, that will converge to dominant eigenvalue. The largest number which we are dividing, that will converge to the dominant eigenvalue. So in that way, by repeating the procedure, we can find both eigenvalue and eigenvector, and that eigenvalue will be largest in magnitude. And since this is an iterative method, we will put a stopping criteria. So you can put any stopping criteria. You can put stopping criteria on eigenvalue. Okay, so you can compare two lambda. So let's say lambda k is an approximation of eigenvalue at kth iteration, and that is lambda k minus 1, eigenvalue k minus 1 iteration. So that is less than epsilon, you can stop. Or you can divide with lambda k to write approximation in terms of relative error. Both we can use. Okay. Also we can use stopping criteria in terms of eigenvector. So since x is eigenvector, so we will take its norm. So we will find absolute error by comparing two iterates if this is less than epsilon, or in relative error we can divide with norm of next iterate xk. So xk is the value of eigenvector at kth iteration, and epsilon is the tolerance that we will predefine, and you can say that is the desired accuracy that we want. Okay, so you can also write stopping criteria in relative error for eigenvalue also, and we assume in numerical method that new answer is better than previous one, so we are dividing with lambda k, that is value of the eigenvalue at kth iterate. Okay, So method is just simple. Ax, so apply A on x, scale x and find new eigenvector. After some time you will see that you are multiplying A with x, you are getting lambda times x. So that number will be the eigenvalue and that x will be the eigenvector. Let us take one example. Let us fix the iterations. So calculate 4 iterations of power method to find dominant eigenvalue and corresponding eigenvector, which we also say that dominant eigenvector for matrix A, which is 3 cross 3. So 1 minus 2 1, 2 1 3, 0 2 1. So let us start with one initial guess of dominant eigenvector. You can take a vector with norm 1. You can take 1 0 0, or you can take 1 0.5 1, or you can take simply 0 0 1, or anything with norm 1. So here I'm writing, so I'm taking 1 1 1. Okay, anything you can take. So I'm taking it 1 1 1. So then multiply A with x naught. This is usual matrix multiplication. Say this is y1, new answer. So 1 minus 2 1, 2 1 3, 0 2 1. So we got first answer 315. So this 315 don't have norm 1, so we scale it. We take 5 largest component outside, so you got 3 by 5 inside. 3 by 5 is 0.6, 1 by 5 0.2 and 5 by 5 1. And in my notation, this is the lambda 1 x1. So if I stop at first iteration, then 5 is the eigenvalue and this vector x1 0.6 0.21, this is eigenvector. But we will continue, okay, to get better answer. So again we multiply this, so we get second answer y2, that is A x1. So matrix A, again I'm writing it 1 minus 2 1, 2 1 3, 0 2 1. So A times x1, so x1 is 0.6, 0.2 and 1. So I got second answer, that comes out 1 1 2.2. So largest 2.2 you can take outside, so I got 0.45, 0.45 1. So in notation, that is 2.2 is my next approximation of eigenvalue, and this is x2 eigenvector. So let's continue. Y3, that will be A times x2. Okay, so that answer, I'm writing this answer, so that is 1.35, 1.55. Just multiply A with x2, 2.8. So 2.8 you can take outside, so 0.48, 0.55 and 1. So in my notation, that 2. So this is third iteration, so I should write lambda 3x3. Let's write this is lambda 3 x3, and you can see 2.2, 2.8 they are not close, but after some time we will get these lambdas close to each other. So let's write next iteration y4, that is just a x3. So multiply a with that x3, this vector. So this comes out after taking outside. So 3.1 you take outside, so this is the final answer, 0.51 and 1. So in my notation, that is, so if I stop here, so this is eigenvalue and this is the eigenvector. So let us say I am stopping after 4 iterations. After 4 iterations, so dominant eigenvalue is 3.1, that is our final answer, and dominant eigenvector is x4, so that is 0.51, 0.51 and 1. And if you do more iterations, after some time this will become 3, I guess, and eigenvector will be 0.5, 0.51. And you will observe that these numbers you are taking outside, they will be close to each other, and eigenvector also become constant. Okay, so first component will become 5.5, second will become 0.5 and third will become 1. Okay, so this is a very simple method that you can apply to find eigenvalue and eigenvector. Let us take one more example, and now we will put a stopping criteria to stop. So let's take find dominant eigenvalue. Find the dominant eigenvalue and corresponding eigenvector for matrix, and I am again taking 3 cross 3, that is 1 0 0, 2 minus 3 0, 3 9 minus 0.5, and you can see this is an upper diagonal matrix, so eigenvalues are just diagonal entries, and these eigenvalues are 1 minus 3 and 0.5. So power method picks dominant eigenvalue in magnitude, so dominant eigenvalue in that is called eigenvalue with the largest magnitude. So this method will pick minus 3, and we will see that. And here we impose one stopping criteria. So use stopping criteria. That is lambda k minus 1 less than 0.1, where lambda k is the approximation of dominant eigenvalue at kth iterate. Okay, so when we compare 2 lambdas, so if absolute error is less than 0.1, we will stop. Okay, so you can take any initial guess with norm 1. So I am taking x0 equal to 1 1 1. So now I am writing first iterate y1, that is a x0. So multiply this matrix with initial guess 1 1 1. So first answer is 6 6 0.5, you can take 6 outside. 1 1 0.0833. So in my notation, this is 6 is first approximation and that vector is x1, first approximation of the eigenvector. Now we continue. Now we multiply this matrix A. So instead of x0, write this 1.0833 in the same way. So you got your answer 3.25 minus 2.25, 0.041667. So largest is 3.25. I am taking outside. So you got 1 minus 0.6923, 0.01282. So this is lambda 2 x2. So now we have two lambdas, lambda 1, lambda 2. So try to find absolute error, that is lambda 2 minus lambda 1. Here k just count, so you can put anyway. So just maybe you can write in that way, or so this is just iteration count. So lambda 2 minus lambda 1 you can compute, that is 2.75. This is bigger than 0.1, so we need to continue. So write y3, that comes out ax2, and that answer is 2.1923 minus 0.15789 1 and 0.002924. So I say this is lambda 3 x3, and now I compute error, that is lambda 3 minus lambda 2, that comes out 1.0577, still bigger than 0.1, so we need to continue. So in next iteration I am writing fourth iteration, so y4, that is ax3. After multiplying, so since we have negative eigenvalue, so largest is minus 2.97, so we can pick largest component with sign, there is no problem. If you don't pick with sign, then at the end you have to fit in the equation that a minus lambda I equal to 0. Okay, let us say you got lambda 3. If you are not picking with sign, so you need to fit 3 and minus 3 both. So which lambda satisfy this equation, so that is the eigenvalue. But it's better that you can pick largest component with sign. So minus 2.97, 37 is largest, so remaining is 0.62241 and minus 0.304916. So this is my new lambda 4 x4, and I compare two lambda 4 minus lambda 3, that difference is 0.7814, still bigger than 0.1, so I need to continue. So now I write y5, that is just ax4. So usually multiply a with new answer, so final answer is 3.0044 and eigenvector is 0.45801, 0.308182. So this is lambda 5 x5. Now I find lambda 5 minus x5, that difference, sorry, not x5, lambda 4, that difference is 0.03, which is less than 0.1, so you can stop. So with this notation, dominant eigenvalue, that lambda is minus 3.0044 and corresponding eigenvector, that is called dominant eigenvector, that is x. So this one, this vector x5, so that is minus 0.45801, 0.308182. Okay, so lambda 5, that final answer at fifth iteration is minus 3.0044, that is largest eigenvalue, and eigenvector that you got, that is x5. So this is a simple procedure which picks both eigenvalue and eigenvector, and recall that this is an iterative procedure. So we need to put an appropriate stopping criteria, either in term of eigenvalue, you can compare two lambdas, or you can compare two eigenvector. And further we will see that you can apply this method, you can modify this method to pick other eigenvalue, and that we are going to study in next class.